our world and beyond. Space, in partnership with the European Space Agency.
In life, everything comes to an end. It's true for humanity as it is for spacecraft. At ESOC, the operations centre of the European Space Agency in Darmstadt, Germany, the final moments of a satellite pioneer, the European Remote Sensing Satellite, ERS-2, are being monitored and controlled. Its operational life ended on the 3rd of July 2011. Deorbit operations then began.
We are now actually approaching the final phase. The first two phases were just dedicated to lower the orbit step by step. We have reached our target altitude of about 570 kilometers. The last point is now to getting rid of all energy resources on board, energy sources, and also all pressurized systems.
The timing is critical. In order to avoid any risk of explosion, all the fuel, hydrazine, which is extremely combustible, must be used up.
And that's only to be done at the last point of the deorbiting activity, which is emptying the tanks. Then we have to quickly react, to switch off the batteries, switch off the transmitters, and that's basically the end of the mission.
Switch over to
ERS will remain on this low orbit, causing no danger to other spacecraft. Within 15 years, it will eventually disintegrate in the atmosphere. The ERS story began in July 1991, more than 20 years ago, with the launch of the rocket Ariane 4, which carried ERS-1. Then, in April 1995, ERS-2 was launched. The two satellites, 12 meters long, were practically twins, although the baby brother had more observation instruments on board and, for the first time on a civilian observation satellite, radar. That allowed it to observe day and night, and also through the clouds. A primary mission was to study the oceans and ice fields, sending back data. The Nansen Center in Bergen, Norway, was closely involved in this work, studying and verifying the quality of the data sent back by the ERS.
We were responsible for a lot of the ice, not necessarily calibration, but validation. So we went up there with icebreakers, and one icebreaker, and a normal ship, and some airplanes. And we had people on the ice making drilling in the ice, looking at the surface structure, and then see what you get from the satellite. And from that one, we can make mathematical formulas and then derive from space what type of ice we have.
In polar orbit at an altitude of 780 kilometers, the two satellites went around the Earth in 100 minutes. They worked in tandem until the disabling of ERS-1 in March 2000. Its twin continued alone to fulfill its mission. At ESRIN, the Centre of Earth Observation Missions of ESA in Frascati, Italy, all the data from ERS has been stored for nearly 20 years.
This started a new era, and originally the concept of ERS was to have a satellite for ocean and maybe ice observation. But it turned out that it became the standard instrument for all geosciences. So we attracted thousands of scientists and scientific projects with this satellite.
Satellites are essential for the overall study of our planet. As they return periodically to the same place, they can, over time, provide mathematical formula for temperatures, winds, and the composition of the atmosphere. ERS-2 was particularly efficient in calculations for sea levels.
It was the first time that we could measure worldwide the sea level rise with this satellite. So we got valuable information now over 20 years time series to see that the sea level, the rate of sea level rise has increased from maybe 1.6 to 3 millimeters per year. You see, these satellites have started a lot of activities in Europe and a lot of successor missions.
With the mix of various instruments on board combining the altimeter, temperature, imagery and land cover, great advances were made mapping inaccessible areas. Take the example of Mount Cameroon. Before ERS-2's observations, the mapping was very rough. With each pass of the satellite, one piece of information was added until the area was mapped precisely. In 1980, the accuracy of the cartography was around 1 square kilometre. After ERS-2, it was increased 1,000 times. Mount Etna, which is well known, is another example of the versatility of the observations from ERS. Using data collected over a decade, it was able to produce a graph to show the movement in the cone of the volcano. To get such results, there are a whole range of instruments on board.
The ERS-2 satellite has 4 instruments. One is the GOME. The GOME measures the atmosphere, the chemistry in the atmosphere like ozone, NO2. The radar altimeter is measuring precisely on centimeter level the surface of the oceans. Then you see after the ATSR, which measures with the infrared instrument precisely on 0.1 degree the temperature of the oceans. And the most characteristic part is this antenna up here. There you have the radar antenna, which makes images also when it's dark and through the clouds. And you have this horns here, which is really unique. And this is the scattorometer measuring the wind speeds over the oceans.
With these instruments, it is possible to see, to study and to quantify the flow of the glaciers in the Arctic and Antarctic. As they melt and flow into the sea, it helps with the study of the ocean. The Nansen Center is named after the famous explorer and Norwegian diplomat who, in 1895, set out to use the natural drift of the ice cap to reach the North Pole. The expedition was only a partial success, but his name lives on. This area is given over to the study of the dynamics and physics of ice, ocean and winds.
With ERS-1 and ERS-2, we have in total had nearly 20 years of observations. And it has been the possibility to see the changes from one observation to the next continuously over this duration that has really allowed us to completely understand the observations, convert the data into meaningful geophysical understanding. And without these 2 satellites, we would not have been today in a situation where we are with numerical weather prediction and ocean forecasting.
To be able to observe in all weathers is an asset in the Arctic, where global warming is opening up new shipping routes. That is when the radar instruments come into their own.
Altimetry is maybe the most simple of these instruments. It looks straight down and it measures the height of the satellite above the ocean surface. And with that observation, we can reconstruct 3 important parameters: surface currents, surface wind, and surface waves.
The images provided by the altimeter data are used to develop interactive maps.
We see several interesting features, many related to ocean currents that we see here, meandering contrast patterns, but also we see clearly patterns of wind here close to the coast. For example, here we see the winds coming out on the fjords, and we see jets, stronger winds and less strong winds. And from this image, we can quantitatively calculate the wind, as seen here in this column map. The arrows show the wind direction coming out here, and the wind speed is up to 50 meters here in the red, yellow areas, and down to 5 meters in the blue. So there are quite strong wind gradients here over short distances. We can also compare this with the model wind that we see here. This is from the NCEP model. We see at a much coarser resolution, and we don't see the fine details as we see on the SAR image. So this is one of the reasons why SAR is a unique resource for this kind of high-resolution wind mapping.
Since 2002, an 8-ton satellite has taken over. It is called Envisat and has 10 integrated observation instruments, some of which are derived from ERS. Soon, next-generation satellites will be in orbit. These are the Sentinels of a joint program between ESA and GMES, the European Union for Global Monitoring for Environment and Security.
Well, GMES will be in the first generation constellation of 7 satellites, with which we look into very different parameters of the Earth, starting with the sea, with ice, atmosphere, land cover change, land use change. So many of the important, environmentally important parameters will be available then in a constant flow of data.
The new satellites will be equipped with more modern and efficient instruments. But it is important not to forget the work of ERS-1 and ERS-2, which have given us a better understanding of global warming and the continued melting of the North Pole ice cap. Their legacy is huge.
Now the work really starts. So we have a satellite, we have 20 years, we managed to have a successful mission from the beginning to the end. We didn't lose a satellite, we always maintain control, but there are 20 years of data in the archive. So these data must be processed, reprocessed again. We must ensure continuity with the futures. This is a heritage for mankind in the future, this high precise measurement. And we have to maintain, preserve these data, and we also have to adapt the mission now, the exploitation of the modern technologies.
It is the 5th of September at the Operations Centre of ESOC in Darmstadt. The atmosphere is one of sadness. ERS-2 engines have burned their last hydrazine. All systems have been disabled. Our satellite has completed its long programme of 3.5 billion journeys around the Earth. In the next 15 years, it will turn into heat and light.